Hi all and welcome to the physics fast load generator demo. The aim of this demo is to introduce the set rate load generator that was produced in the context of the physics project, which is implemented as a NodeRed flow, includes a relevant subflow for this reason, and as such it can be used directly inside NodeRed if one is not interested in too much scale over load generation, or if one is interested in very scalable load generation, they can use the function mode that embeds this subflow inside an Openwhisk action and launched in a cluster that includes Openwhisk. The flow has been published in the NodeRed repository, and it's also available as a Docker image on Docker Hub. So some internals about the load generator. The most important characteristic is that it supports the function chaining aspect. So this is needed because typically functions in fast frameworks have strict timeout. So if the experiment duration that is needed is above that limit, then one needs to implement the pattern of the function chain. The main details of this pattern is that the input data trigger the execution of the first function. Inside the first function, a monitor needs to exist in order to determine if it is near the timeout. If it's near the timeout, then this function is responsible for invoking a successor function, passing it any initial arguments that are needed, as well as the output of the first function. The same applies for each function after that, and at the end of the execution, the final function needs to do any post-processing, wrap up the results, and take under consideration any intermediate results that have been produced in order to provide the final output. Here is an overview of the subflow used to implement this pattern. So the most critical part here is that the function itself needs to be designed in such a manner so that any external monitor can understand what is the status of the function, how it has created the successor function, what is the successor function, and so on. So in that case, the function itself, the first function, needs to store a status in the if it hasn't finished, if the timer hasn't finished, it needs to invoke the next function, and it needs to store in the results what is the activation ID of the new function, as well as the relevant status message. Then an external client that polls for the result can check the outputs of the initial function and carry on the monitoring to the new activation ID that has been stored as a result of function 1. So now the external monitor can proceed with monitoring function 2 and so on. In terms of metrics that we support, a large number of different measurement points are included in the load generator. So from the parent sample time that is provided by the initial caller, the initial caller can create one or more functions to create the load, and then there are different timestamps that are taken inside the process, from the actual start time of the load generator to when each individual call is being done towards the external system, in this case a fast system, namely Openwhisk. And then, exploiting also the monitoring abilities of Openwhisk, we can retrieve also aspects such as the wait time inside the system, the initialization time for the container to execute the function, as well as the duration of the function itself. So from that we can calculate various statistics like averages, deviations, etc. of the start latencies, so from the client sample time up to the start time that is reported by Openwhisk, the function start time. We can also measure the overall total user side delay, and from that Also, if we subtract the wait, init, and duration time, we can also estimate the network latency. Also, we can have other calculated metrics to check the individual sample times that the client generates in order to validate the achieved rate that we have in the experiment. And also, if we have multiple different functions, to check the start times in order to validate that we have, let's say, indeed 4 or 5 different functions generating load at the same time. As an example input in the load generator, we won't go through all the fields. You can include the test name. This is one of the most important, the inter-request delay for its invocation, in this case 6 seconds. What is the overall test duration? If you want to include any client IDs inside, credentials for the Openwhisk installation, because we need to obtain results and so on. What is the method we want to use against target endpoint? What is the function that we want to invoke as a parameter of the load? If we need the post method, what is the payload of that method? Where we can get the status, and where is the let's say the function, the load generator function, if you want to use the fast mode, the NodeRed mode. So in that case, we need also to select this specific option here. If we want to use the execution inside NodeRed server, then we can use the local option. The parent sample time and global sample time, this should be identical initially in the input that we provide, and it should be a timestamp just before we do the call. So let's proceed with the practical aspects of the implementation. We have a helper flow. This helper flow includes an initial client that does the initial function invocation, and then we have the poll to push converter. This is another flow that we publish through the physics NodeRed collection for getting the result and for monitoring the progress. So let's go ahead and start the experiment. So the experiment now has started. The options that we have is that we set the experiment to run for 360 seconds. This is above the maximum 300 seconds of the Openwhisk timeout. So this should trigger a chain activation as well. While we are waiting to finish the experiment, let's look a bit on the internals of what happens in the OpenShift backend cluster. So you can see that the load generator function has been launched, and it has also started generating requests towards the target function. In this case, a simple sleep action that we have implemented. So let's go to the logs and see what happens in the load generator. So we see the inputs that we used. And now you can see this is the timer inside the flow that self-monitors the function if it is near the completion. So currently this limit is set to about 220 seconds. So when the 220 second marker gets passed, it will trigger this specific function to start preparing the successor, call a new function in order to carry on the load for the remaining of the test duration. Okay, so we have all this self-monitoring of the activation. Let's wait to see what happens in the end, about 220 seconds after that. So as mentioned, the critical point is for the function itself to log what is the successor function. So it needs to call the new activation, the new function, retrieve the new activation ID and store that activation ID in the results, so that then when the pull to push converter that supports function change gets the results of the initial function, it can check the new activation ID and then follow up on the new activation ID for the results. We are now near the completion of the initial function. Okay, so we see a lot of log outputs here. These are the overall outputs, and you can see that with the limit, we are preparing now the new activation, and we should be triggering another action. One interesting thing is that we include also the raw data. Why? Because the raw data need to be available in the final function in the chain in order to calculate all the statistics that we need, such as averages, standard deviation, etc. Okay, so we include all of this, and the result includes also the new activation ID in order to follow up on the execution. So let's go to the successor function. So you see we have the previous function that just finished, and now it's the next function in the chain. If we go to the logs, you see now that the execution follows on for this function, but it keeps track of the overall experiment duration that we have set at the beginning. So at the beginning we said about 360 seconds to run. So we should see the remaining execution from the first 220 seconds. The remaining seconds up to the 360 will be undertaken by this specific function. We should be near the completion now, around 130 or 140 seconds. Okay, so we see that the overall test duration from the beginning of the first function has been 361 seconds. The limit was about 360 seconds. So now we produce the final output. So let's go and see the final output. This is our initial flow, and this is the final message that we get. Okay. So inside we get various stats. What we are interested in mainly is the response of the final action. This action has included the raw data from all the previous executions and has calculated various statistics like the achieved average rate that we wanted, what action we called as the target action for the load generation, actual start time, the response time, the average duration of the function, the average initialization time, start latency, total user side delay, wait time inside the system, and so on. How many call starts, memory used for the function that we are targeting. What was the set rate? We had the set rate of 10 and we had an achieved rate of 8.31. If we used a bit of larger duration, we could get much closer to the set rate. And the standard deviation of the various metrics, success percentage, etc. It also gives back the raw data in order for someone to, let's say if they want to validate the results, if we want to do some other form of processing, we have the raw data of each individual call processing. So thank you all for watching. You can find more information on our project website. The list of collections from the physics project in the NodeRed repository can be found in this link. Also, a lot of the images that were used, including the delay action image and of course the load generation image, can be found on Docker Hub. And if you have any questions, don't hesitate to contact us.